Hi, I'm going to be talking about our work, robust resource allocation via competitive subsidies. I'm David Lin, and this is work with Giannis, Fikioris, Sid Banerjee, and Ava Tardos. So we're going to consider an online repeated allocation problems. So just to illustrate the sort of setting that we're going to consider a setting in which there's a resource to be allocated, in this case illustrated by a computer, and the resource is to be allocated among a fixed set of agents, David, Giannis, Sid, and Ava in this case. And time is going to proceed in discrete time steps. And at each round, each agent's going to draw some value for the resource. And we're going to consider a scenario where the principal has to decide which agent to allocate the resource to without direct knowledge of the agent's value. So they're going to have to somehow decide to, say, allocate it to Sid. And this is going to repeat. So every round, agents are going to redraw values for the good or item, and the principal is going to redecide who to allocate it to. In this case, maybe Giannis. Okay, so this will continue, maybe David, and again, maybe David again. Um, and so, more concretely, the setting we're going to consider is we're going to have a fixed set of n agents and capital T rounds. So we're going to consider capital T very large to consider a large time horizon. And each round, a single goods to be allocated. And the way the values are going to be drawn, so each agent's going to have a fixed value distribution. This will be fixed across rounds, and values will be drawn i.i.d. from the value distribution. We're also going to assume that values are drawn independently across agents. And we're going to assume that agents uh, utilities are additive across time, so they're simply trying to maximize their total utility summed over time. And the goal is will be to design a mechanism in which agents can participate to give a fair and efficient allocation. And again, we're going to assume the mechanism does not have direct knowledge of the agent's values. And we're also going to assume that we're in a setting in which we're not allowed to use monetary transfers. We're not allowed to charge the agents money. This sort of online repeated allocation setting has some real life examples motivating it. Many of them listed on the side. For example, allocating competing resources to labs at university, allocating medication or equipment to hospitals or patients, allocating humanitarian aid, parking spots, vacation periods, etc. And yeah, like in all of these scenarios, we want to find fair and efficient repeated allocations without charging money. So one problem with evaluating fairness and sort of what objective we should maximize is that agents' values are incomparable. So different agents have different value distributions. It's unclear what some agents' numbers mean to compared to others. For example, some agents might just have much higher values than others simply because they're measuring values in sort of a different unit. Like maybe their values are just like 1,000 times what someone else might report. And so if you want to figure out what you should optimize, like doing some aggregate measure, like maximizing the sum of agents' total values, like summing them all up, may not lead to a fair outcome because that would bias towards those who report higher values. And so if we want fairness, we're going to instead consider an individual benchmark and compare against that. The individual benchmark we consider is called ideal utility, which has been introduced in a paper in EC21 by Arthur Gorak, Sid Banerjee, and Chris Iyer. And the way you should think about agent I's ideal utility is the utility agent I would receive if like the highest utility they could possibly receive, except they're only allowed 1 over n fraction of the rounds, like their fair share fraction of the rounds. Because so this would essentially be the utility they would receive from their favorite 1 over n fraction of the rounds, their highest valued. And maybe you would want to try to design an allocation procedure in which every agent achieves their ideal utility, but this isn't possible because different agents' top valued 1 over n fraction rounds may conflict in that they overlap. And in each round, you can only allocate the good or item to like a single agent. So if agents top 1 over n of the fraction of the rounds overlap, it won't be possible to give everyone their ideal utility. Instead, we're going to try to approximate it. So if we're going to try to, for fairness purposes, give everyone a high lambda fraction of their ideal utility for some high lambda. And due to these conflicts, you can show that the highest possible lambda you could possibly hope for, even if you could see all the values in advance, is this 1 minus 1 over e, or about 0.632. And this comes from worst case value distributions. If everyone has a value distribution like Bernoulli 1 over n, you can use some sort of like balls and bins argument to show it's not possible due to conflicts to have a higher fraction of ideal utility than this 0.632. Um, so that was what we should try to do for efficiency and fairness. Uh, we're going to talk about how agents actually behave in a mechanism. And so the goal that we're going to try to accomplish is we're going to try to design a mechanism in which each agent has what we call a robust strategy. Specifically, a lambda robust strategy is a strategy that they can use to play in the mechanism to guarantee themselves a lambda fraction of their ideal utility, regardless of the strategies of others. So more formally, we define lambda minus little o of 1 fraction of ideal utility with high probability, where the with high probability and the little o of 1 are with respect to the time horizon. So it should be approaching a lambda fraction of ideal utility with high probability if the time horizon is large, which we're going to assume. Um, and so a robust strategy is a rather strong requirement. So regardless of strategies of others, this means that like even if other agents say disregard their own utility and collude to harm a specific agent, if that agent is following a lambda robust strategy, even if others are colluding against them, they should still obtain a lambda fraction of their ideal utility. And this sort of setting and this notion of lambda robust has been investigated before. So um, at the start, there's this paper GBI 21, the EC 21 paper I previously mentioned, that first gave a mechanism in which there's a robustness factor of half for some strategy. And then later, my co-authors gave a different mechanism that also achieves this half robustness. And then recently, we also gave a third different mechanism that achieves a robustness of half. Last year in ITCS 25, we and Daniel Hall, an undergraduate at Cornell, used the mechanism of GBI 21 and gave a slightly better strategy that improved the robustness to 0.585. And actually, in this work, we're going to give a new mechanism that has a strategy with a robustness of 0.625. So this improves on all the previous robustnesses. And the mechanism we're going to propose, we call the competitive subsidy mechanism, which works as follows. So each agent is going to get T over N units of artificial currency at the beginning. So every agent gets the same amount of artificial currency. And in each round, agents can do one of two things. They can either bid or not. And the winner will be selected uniformly random among those who bid for the item. And the winner will pay some amount. So they'll pay B bar times K over K plus 1. So B bar is just a constant, where K is the number of bidders. So they pay this amount in artificial currency, and once agents run out of artificial currency, then they just won't be allowed to bid anymore. And just for some intuition behind this payment rule, like notice K over K plus 1 is increasing in the number of bidders. So this is some sort of congestion pricing where the winner pays more the more number of people who bid for the item. And so now our main result for our robustness is we're going to suggest that each player use a simple threshold strategy, which is just bid whenever their value is sufficiently high. Specifically, sufficiently high means the value is in the top 1 over n quantile of the value distribution. And we're going to show that if you set B bar appropriately to around 2.67, then this is how we get our 0.625 robustness. Um, and before we get into sort of proof, just some motivation behind the competitive subsidy mechanism. So the first sort of mechanism studied in this setting was GBI 21, which they considered just repeated first price auctions with artificial currency. So everyone was endowed an equal amount of, in this mechanism, everyone was endowed an equal amount of artificial currency. And in each round, each agent bids some amount of artificial currency, so they can name any like real amount of artificial currency. The item will be allocated to the person who set the highest value, and they pay that amount. And so our result in ITCS 25 gave a 0.585 robust strategy in this mechanism, which just followed the simple strategy of whenever the value is sufficiently high, the agent is going to bid from a certain uniform distribution. And otherwise, they're not going to bid, they're going to bid zero. And the way we thought about this is like, okay, suppose every agent follows some strategy like this. So they either bid from this uniform distribution or they bid zero. Like, what would happen in this case? Well, in each round, if there's k bidders, meaning bidding from this uniform distribution, then each bidder is going to win with probably 1 over k just by symmetry. And the winner is going to pay in expectation the expected maximum of k i.i.d uniform random variables, which is exactly b bar times k over k plus 1. And this is exactly sort of what the competitive subsidy mechanism is doing. So in the competitive subsidy mechanism, you have artificial currency, but you can't bid just like any real amount. You can either bid or not. And in the competitive subsidy mechanism, it does exactly this. So each bidder is going to win with like 1 over k probability, just uniformly at random, and they're going to pay exactly b bar times k over k plus 1. This is the payment rule in the competitive subsidy mechanism. So the competitive subsidy mechanism is sort of emulating a repeated first price auction scenario where each agent is allowed to bid from this uniform distribution or not. And that's all they're allowed to bid. And so why should you want to restrict the bidding like this? Or what's so good about this? Well, first notice that in the competitive subsidy mechanism, I should at least still have a 0.585 robust strategy because I can still follow this strategy of bidding whenever the value is in the top 1 over n quantile or not. And like 0.585 robust for the repeated first price auctions, uh, means that like if you follow this strategy, regardless of the strategies of others, you'll gain a 0.585 fraction of your ideal utility. So this is still true in the competitive subsidy mechanism because I can still follow this sort of strategy. But actually, you can further potentially increase the robustness to something even higher because you're restricting the strategies of others. Like others don't have um, as many strategies that you need to play against. So potentially the robustness factor will increase. And that's essentially what's going on in the competitive subsidy mechanism, which is why we're able to get the higher robustness of 0.625. So now I just want to get into maybe a little more formal of how the proof actually goes for why the robustness actually increases formally. So again, our strategy is the agent I will bid when the value is in the top 1 over n quantile of the value distribution. The way you should think about robustness is like you want to say no matter what happens with the other agents, you're going to get some fraction of your ideal utility. So in the worst case, you should think of other agents as an adversary trying to harm agent I. So they're an adversary, so maybe they're going to pull all their budget together. So their total budget is 1 minus 1 over n times t. And at each time they have to decide what to do. And because each agent can only bid or not, they only have so many things they can do. Basically, at each time t, they have to select KT agents to bid at each time subject to their budget constraint for some KT. And actually, you can show that the optimal adversary strategy is just to bid one agent at a time until they're out of budget. And now with um, with this sort of strategy, like you can sort of calculate what will happen because agent I is following a simple threshold strategy. Adversary is the other agents are just following the simple bid one agent until out of budget. You can calculate the fraction ideal utility agent I gets under this scenario in terms of B bar, which was the constant in the payment rule. And then you can show if B bar is too high, then people are spending too much, in particular agent I will be running out of budget too quickly, so this will be bad for them. And if B bar is too low, then the adversary has too much budget to potentially harm agent I, so that won't be good. And there's some middle ground, 8/3, that will lead to our 0.625 robustness. And so that's how we get our robustness result. Um, so now I want to talk about maybe more realistic behavior assumption, which is equilibriums. So before robustness was talking about what fraction ideal utility agent I can get when the others are colluding to harm agent I. Well, maybe we don't want to make such an extreme behavior assumption. Maybe we want to consider equilibrium where everyone is acting in their own self-interest. So the first question we might have is, do the robust strategies that uh, we propose form an equilibrium, and that if everyone plays it will be an equilibrium? And actually, the answer is no, at least if we set B bar as proposed on the previous slide. Because if you calculate what happens when everyone plays that strategy, you can show that agents aren't spending their budget fully, meaning they have some leftover budget that they should deviate from the strategy profile to potentially gain more utility. And we're going to show how to make this into an equilibrium. And the main idea will just be if you set B bar slightly higher to around 2.72, you can show that if every agent follows this strategy profile, that agents will be spending their budget exactly. So it won't be so obvious that they're not playing an equilibrium. And well, let's just try to see if now with this new B bar, if the robust strategies actually form an equilibrium. So yeah, we're going to set B bar slightly higher. And to analyze whether it's in equilibrium, we want to analyze whether agents want to deviate from the strategy profile or not. So because every agent in each round can either bid or not, roughly speaking, deviations can only occur in one of two ways. Like either an agent can bid more or bid less often. So actually, no agent really wants to bid more often because by bidding more often, they'll be winning more often, and so they'll be losing budget more quickly. And actually, because they'll be blocking other agents more often, in that if you bid more often, other agents will lose more often. They'll actually end up losing less. So the other agents won't be paying anymore. And so all you're doing by bidding more often is you're being less selective about which rounds you want to win. And you'll run out of budget quicker and you'll get less utility than if you were more selective about what rounds you can win and have a higher sort of threshold for the value you want to win. So you should not deviate by bidding more often. Actually, we couldn't prove that you don't want to bid less often if your value distribution is a little bit weird. Like if your value distribution is Bernoulli 1/2n, then you actually do want to bid less often. So our strategy we suggested was to bid whenever your value is in the top 1/n quantile of your value distribution. But if your value distribution is only 1 with probability 1/2n and 0 otherwise, our suggested strategy profile says that sometimes you should be bidding with value 0, which sounds like a little bit of a silly thing to do. And in fact, it is a silly thing to do because if you were to, instead of bidding when you have value 0, just don't bid, then others will be winning those rounds more likely that you have value 0, meaning they'll run out of budget quicker. And then maybe at the end, when you actually have value 1, others will be out of budget, so you'll be more likely to win those rounds. So actually, this strategy profile as is not in equilibrium if we have value distributions like Bernoulli 1/2n. But actually, we have this sort of simple fix, which is, well, we're going to change the mechanism such that if agents aren't bidding with high enough frequency, the principal will just force them to bid. Specifically, we want them to be bidding with probability 1/n, so we say by time little t/n, you should have bid roughly little t/n times, otherwise the principal will force you to bid. And then we actually get an equilibrium, because then you don't want to bid more often, and we force that you can't bid less often, so uh, the strategies that we suggest will actually form an equilibrium. And you can actually show it's an optimal equilibrium in the sense that everyone gets a 1 minus 1/e fraction of their ideal utility, which was the optimal possible ideal utility you can guarantee with worst case value distributions. And this is just, and more or less, it comes from the definition of ideal utility and the strategy profile that we suggest. So this is actually higher than the robustness factor, assuming agents um, behave in equilibrium. Actually, about the robustness factor, because we're setting B bar slightly higher, so before we set B bar to optimize for robustness, if we set it slightly higher than the robustness of the strategy we suggest will actually decrease to around 0.613 as opposed to the 0.625. So that's sort of the cost of trying to make these strategies actually form an equilibrium. And just want to compare it to previous works. Actually, a lot of previous works didn't have equilibrium results in that they had robust strategies that just weren't equilibrium, including like GBI 21, FBD 25. Um, Actually, the only previous work that had an equilibrium was our previous work in SOTA 26, which had a robustness factor of zero point 0.5. So we actually improved this robustness factor while still maintaining we both have an optimal equilibrium. More or less, the reason why these two works are able to obtain an equilibrium is because they have a smaller strategy space. Like in both these works, like in each round, agents can only do one or two things, like bid or not. Um, it's harder to analyze equilibrium when there's a bigger strategy space. For example, if you consider just the repeated first price auctions where people are able to name like any bid, like that's much harder to analyze equilibrium because like others, like given any fixed strategy profile, including like the robust strategy, like others may want to deviate to all sorts of crazy strategies, like bidding arbitrary amounts or bidding different amounts in like different rounds and changing the bids, which is allowed in repeated first price auctions, but in our competitive subsidy mechanism, because you can either only bid or not, we don't have to analyze so many types of deviations. And that's essentially why we're able to obtain an equilibrium. So, in conclusion, today we saw the competitive subsidy mechanism, which is sort of this mechanism with artificial currency, but in each round you can only bid or not. And the winner is going to be randomly chosen among bidding agents and pay some amount, increasing in the number of bidders who tried to bid for the good. We achieved the best known robustness out of all previous works, 0.625, and we also showed how to improve or how to make the robust strategies into an optimal equilibrium at the cost of decreasing the robustness a little higher. And just to end on sort of an open question, like this robustness is not the offline optimal 0.625, the offline optimal being 0.632. And so we have an open question, like, is it possible to improve the robustness? In the paper, we give like very, very strong numerical evidence that you really need a new mechanism that just by changing this payment rule, so this k over k plus 1 function, like if you change it to some other function in terms of k, like that will not be able to improve the robustness beyond 6.625. Um, and so if you want to ask, is it possible to improve this robustness, maybe even towards this upper bound 1 minus 1 over E, you're really going to need some sort of new mechanism. Okay, so with that, I guess thank you for listening.